Hey, it's 11. Today we'll continue in section 3.2 on exponential functions, and we might get to section 3.3 on logarithmic functions. As soon as class is over, or shortly thereafter, we'll have a Zoom meeting. So I sent you the meeting ID to join the meeting at 11:50. The meeting will actually start officially at 11:30, but we won't join it until about 11:50. Okay, so let's continue with graphing exponential functions. Last time we got a rough sketch of the graph of y equals 3 to the x plus 1 minus 3. And just as a reminder, the minus 3 up here corresponds to a vertical shift downward, so the horizontal asymptote is also vertically shifted downward to the horizontal line y equals -3. Okay, this next example, the base number is 1/3. 1/3 is a number between 0 and 1, so that we're expecting a graph that goes downhill as you look at it from left to right. The exponent is x minus 2, so I'll just pick a few ordered pairs of points that are on the graph. And my general strategy is if the exponent is x minus 2, my middle x value is going to be the x value that makes x minus 2 equal to 0. So my middle x value is 2, then I'll pick a couple of integers that are smaller than 2 and a couple of integers that are greater than 2. And let's just start with the middle one. 1/3 to the 2 minus 2 is 1/3 to the 0. 1/3 to the 0 is 1. So the ordered pair 2, 1. When x is, let's do the larger values first. When x is 3, the exponent 3 minus 2 is 1, and 1/3 to the first is 1/3. And when x is 4, the exponent is 2. 1/3 to the second is 1/9. And then when x is 1, 1/3 to the -1 is equivalent to 3 to the +1, or 3. And when x is 0, 0 minus 2 is -2. 1/3 to the -2 is equivalent to 3 to the +2, or 9. So note that the ordered pair 0, 9 is the y-intercept. Okay, so we'll just plot those points. We're expecting a graph that decreases or goes downhill from left to right. Okay, so 0, 9 is a point on the graph. 1, 3 is a point on the graph. 2, 1. 3, 1/3. 4, 1/9. So the graph roughly looks like this. And in the abstract, the graph will never actually touch the x-axis, but it gets as close as you can imagine. So the horizontal line y equals 0, or the x-axis, is the horizontal asymptote. So always remember to think about where the horizontal asymptote is when graphing exponential functions. Okay, now we'll look at a special exponential function, the exponential function with base e. So the number e is referred to as the natural number. So here's a little bit of information. The exponential function y equals e to the x, the base is e, is called the natural exponential function because the base is the natural number e. The natural number e is an irrational number. Its approximate value is 2.71828. So it's between 2 and 3, but it's closer to 3. Its decimal expansion is non-repeating and non-terminating. That is true of every irrational number. And you can approximate the number e using this expression and a high-powered calculator. If you pick a large positive value for m, then 1 plus 1 over m raised to the power m is approximately equal to e. But if you pick m to be a negative number that is large in absolute value, like say negative 1 million, then 1 plus 1 divided by negative 1 million raised to the exponent negative 1 million, then that is also approximately equal to e. That is a useful fact to remember. It might come in handy. We'll sketch a graph of y equals e to the x. This one doesn't have any vertical shift. E is a number that's greater than 1, so it's going to increase. The y-intercept is 0, 1, because e to the 0 is 1, and the negative x-axis is the horizontal asymptote. And when x is 1, e to the first power is e, but e is about 2.71828. Okay, so I put a dot there. That doesn't mean that it's a point on the graph. That's where the number e is about. So the graph goes to those 2 points. So roughly, this is what the graph of y equals e to the x looks like. So you can plot a couple of ordered pairs like 1e and 0, 1. To get a graph of y equals e to the x minus 1 plus 1, this plus 1 on the outside here, or to the right of e to the x minus 1, that implies a vertical shift upward by 1 unit. So the horizontal asymptote will be y equals 1 for this one. And then the x minus 1 in the exponent compared to y equals e to the x, this involves a horizontal shift to the right by 1 unit. So in other words, we'll do the vertical shift of 1 unit, so the horizontal asymptote shifts upwards. So y equals 1 is the horizontal asymptote. And let's just follow where the point 0, 1 on the graph of y equals e to the x goes after the horizontal and vertical shift. So the ordered pair 0, 1 on the graph e to the x, move that 1 to the right and 1 up, we're at 1, 2. So the graph will look roughly like this. So let's find the y-intercept. So we can find the y-intercept if we replace x with 0. So replace x with 0, we get e to the negative 1 plus 1. E to the negative 1 is just 1 over e. So I'll just write it as 1 plus 1 over e. So this is roughly 1 1/3 because e is about 2.7. It's almost 1/3, but not quite. So 1 plus 1 over e is in the neighborhood of 4/3. Okay, let's move on to some exponential functions that are used to compute compound interest. So for this one, we're essentially going to derive one of the compound interest formulas. If we suppose a principal of $P is invested at an annual interest rate of 100 times R%. So what that means is the decimal form for the annual interest rate is R. To illustrate what I mean by what I wrote here, 100 R%, if the annual interest rate is 7%, then the interest rate in decimal form is 0.07 or 7/100ths. And in our calculations of interest, we're using the decimal form of the annual interest rate. Okay, so that's just an illustration. So for this example, P is the number of dollars invested, and the annual interest rate in decimal form is R. If interest is compounded once a year, then determine the value of the investment after 10 years, and then determine its value after T years. Okay, so we say at year 0, that is the point in time when the investment is made. And then 1 year later, since interest is compounded once a year, well, you'll still have the investment that you began with plus R times P. This is the annual interest earned on $P after 1 year. But notice that you can factor P out of both of those terms and write it as P times the quantity 1 plus R. Okay, so at the end of 1 year, you have more than what you started with because you earned interest. You have P times 1 plus R. After 2 years, which is 1 year after the first year, at 2 years, you have what you had at 1 year, P times 1 plus R, plus interest that is earned on P times 1 plus R. And that amount of interest is R times P times 1 plus R. And you'll note that P times 1 plus R can be factored out of each of those terms. So when we factor P times 1 plus R out, well, there's a factor 1 that I didn't write here. 1 is a factor of everything. So 1 plus R stays behind. But instead of writing P times 1 plus R times 1 plus R, we can write it as P times 1 plus R to the second. Okay, so you no doubt have seen the pattern. Let's just write down what the value is after 3 years. It's the value that we had at the end of 2 years plus R times the value that we had after 2 years. So when we do the arithmetic, we just get P times 1 plus R to the third, and so on. So after 10 years, we see the pattern. This is just going to be P times 1 plus R to the 10th. And then after any number of years, T, the value of the investment will be P times 1 plus R raised to the power T. Okay, so that is the compound interest formula if interest is compounded just once a year. We'll look at a couple of other compound interest formulas. But we'll define the terms first, define the variables. Okay, so capital P at least when investing, capital P represents the principal, what is called the principal. It's the amount of money that's invested. R, which we've already encountered, is the annual interest rate in decimal form. N is the number of times the interest is compounded each year. And it's normally expected that the compoundings will be at equal intervals. And T is the number of years since the initial investment. And for these formulas, I'm using capital B to represent the value of the investment after T years. Well, we derive this formula. If interest is compounded once a year, then the value of the investment after 1 year is P times 1 plus R raised to the exponent T. If interest is compounded N times a year, at regular intervals, then the value after T years is P times 1 plus R divided by N raised to the exponent N times T. This formula is not that hard to derive. It takes a little time, but it's not hard. And then we have a compound interest formula for when interest is compounded continuously. And so by continuously, that means that every instant, perhaps every nanosecond, the interest is compounded. So the value after T years is P times E to the RT. If we ever get time, I'll show you how to derive this formula, the continuous compounding of interest formula. Okay, we'll practice writing values of investments when the interest is compounded a different number of times per year. So in this situation, we're supposing $12,000 is invested for 14 years, and the annual interest rate is 9%. Then the value of the investment, if interest is compounded annually, once a year, well, the principal is 12,000, and we multiply that by 1 plus the decimal form of 9%, which is 0.09. And the investment is for 14 years, so the exponent is 14. So for my quizzes and tests, this is a perfectly fine answer. You could write it a little bit more compactly because it's easy to add 1 to 0.09. So you could write it as 12,000 times 1.09 raised to the exponent 14. For the final example, you're going to be allowed to use a calculator and probably expected to be able to round this number to the nearest 100th or the nearest penny, the nearest cent. Okay, let's do the next one. If interest is compounded monthly, that means 12 times a year. So the value of N is 12. So that means we're going to use this formula up here, replace N with 12. So the value of P is still 12,000. And inside the parentheses, this time we have 1 plus 0.09 divided by 12. And then the exponent is, according to the formula, N times T. So T is 14 and N is 12. So 12 times 14, that's just 168. But you can leave it as 12 times 14 if you want, or it's okay to write it as 168 also. And as I have said, this will be a fine answer for my quizzes and tests. Then if interest is compounded quarterly, that just means 4 times a year, once every 3 months. So the value of n this time is 4. So the value after 14 years is 12,000 times 1 plus 0.09 divided by 4 raised to the exponent 4 times 14. You could write 56 or just write it 4 times 14. Okay, then if interest is compounded continuously, okay, so here's the formula up here for compounding continuously. So the principal is 12,000 times e to the 0.09 times 14. So you can leave it in that form. Or you could write it as 0.126. Yeah, just leave it in factor form. Okay. Now we'll look at some more examples involving compound interest. Okay, but this time the value of an investment of $4,000 increases in value to $10,000 in 10 years. Find the annual interest rate R if interest is compounded annually. So before plugging in the numbers, I'll just write down the function. So the value after t years, if $4,000 is invested, we don't know the interest rate R, so I'm just going to write 1 plus R to the power t. Okay, so this would be the formula. If we don't know what R is, this would be the value after t years. Okay, but we are told that the value V is 10,000 when t is 10. So we're going to replace V with 10,000. And we set that equal to 4,000 times 1 plus R raised to the 10th, because we're also replacing t with 10. And then we can pretty easily solve this for R. First, divide both sides by 4,000. And when you divide both sides by 4,000, 10,000 divided by 4,000, that simplifies to 5 halves, or 2.5, but I'll write it as 5 halves, equals 1 plus R to the 10th. And then we can just raise both sides to the 1/10th power using properties of exponents. So on the left-hand side, 5 halves to the 1/10th equals 1 plus R to the 10th to the 1/10th. And then remember that one of the properties of exponents, if you have something raised to an exponent, and if that is raised to an exponent, you can multiply those two exponents. So that's why I chose to raise both sides to 1/10th, because 1/10th times 10 is 1, and 1 plus R to the first is just 1 plus R. So to solve for R, we just subtract 1 from both sides, and we get 5 halves to the 1/10th power minus 1. And I don't know how to do that arithmetic in my head, but you can use your calculator if you want to get a decimal approximation of that. Okay, the next one, if interest is compounded monthly, then the value of n is 12. So I'll write down the function first. So the value after t years, we still don't know what R is for this one. So V equals 4,000 times 1 plus r divided by 12. And the exponent is 12 times t. Okay, but in this problem, if you remember, up here, the value after 10 years is 10,000. So we replace v with 10,000, set that equal to 4,000 times 1 plus r divided by 12. And the exponent is 12 times 10, which is 120. So just like in the previous example, we divide both sides by 4,000. 10,000 divided by 4,000 is 5 halves. So 5 halves equals 1 plus r divided by 12 to the 120th. And just like we did before, we're going to raise both sides to the exponent 1 over 120. So on the left-hand side, we get 5 over 2 to the 1 divided by 120. And I'll just write the simplified expression we get when we raise 1 plus r over 12 to the 120th to the 1 over 120. We're going to get 1 plus r over 12. And then we can solve this equation for r in 2 steps. So I'm then going to do both steps at once. I'm going to subtract 1 from both sides, and then afterwards divide everything by 12, or sorry, not divide, but multiply everything by 12. So I'm going to have 12 times a quantity in brackets. Inside the brackets are 5 halves to the 1 over 120 minus 1. And then that's what r is equal to. I'll leave the next example for you. If you do this quarterly, this time the value of n is 4. So the process is the same as for monthly. It's just that instead of 12, you have 4. But otherwise, you could just mimic what happened up here. For continuously, though, the function, the value after t years is v equals 4,000 times e to the rt. And then we're told that when t is 10 years, the value is 10,000. So replace v with 10,000. Set that equal to 4,000 times e to the r times 10, or 10r. Okay, then divide both sides by 4,000. 10,000 divided by 4,000 is 5 halves. So 5 halves equals e to the 10r. And we can raise both sides to the 1/10. So let's go ahead and do that. So we get the number 5 halves, to the 1/10. And when I raise e to the 10r to the 1/10, 1/10 times 10r is just r. So I just get e to the r. Okay, and now what? We want to solve for r, but r is an exponent. Okay, so in order to solve this, we need to know about logarithms. And that is what we're going to discuss in section 3.3. So for now, we'll just leave this one hanging. And then in a couple of days, we'll know how to solve this for r. Okay, so we'll do some application problems. Use exponential functions in applications. So this one says an investment of K dollars loses 1/3 its value every 4 years. find a formula for its value after t years. Okay, so let's make a column for the years, and then a column for the value of the investment. Okay, so when we start out at year 0, the value is K dollars, but then we're told that it loses 1/3 of its value every 4 years. So after 4 years, if K loses 1/3 of its value, then its value is just 2/3 times K. Then after 4 more years, after 8 years, the value after 4 years loses 1/3 of its value. So its value after 8 years is just 2/3 of 2/3 times K. And then at the end of 12 years, the value after 8 years loses 1/3 of its value. So there's only going to be 2/3 of this value left, which is 2/3 times 2/3 times 2/3 times K. So perhaps you see an exponent, or see a pattern involving exponents. So let's go back up here. After 4 years, we can think of this as K times 2/3 to the first. After 8 years, think of this as K times 2/3 to the second. After 12 years, this is K times 2/3 to the third. And we can even go back to year 0, because 2/3 to the 0 is 1. So we can think of this as K times 2/3 to the 0. Okay, so I'll show you one more thing based upon what we're looking at. After 4 years, the exponent on the base number 2/3 is 1. So this is K times 2/3. Let's see. How can I use the number 4 in a fraction so that it's equal to 1? Well, if I divide 4 by 4, I get the exponent 1. After 8 years, how do I use the number 8 in an exponent in a fraction so that it's equal to 2? Well, if I divide 8 by 4, I get 2. 8 divided by 4. So no doubt you see the pattern now. After 12 years, this is K times 2/3, and the exponent is the number of years 12 divided by 4, because it takes 4 years for the reduction by 1/3 to occur. Okay, so we can see what the value is after any number of years t. The value after t years is K times the base number 2/3, and the exponent is t divided by 4. And you can always verify that your formula is correct by using it in situations that you know what the values are. Okay, so this is something that you should know how to do. Know how to do this. Okay, then the next example is similar in a way, pretty similar, but this time the investment grows instead of loses. So this one says an investment of $M doubles in value every 7 years. Find its value in t years. Okay, so if you understood thoroughly what happened up here, you could say, well, I know what the formula is right off the bat. But we'll go through the motions. We'll write a column for the year and a column for the value. At year 0, the value of the investment is $M. And then in 7 years, the value doubles. So after 7 years, we have 2 times $M. Then after 7 more years after that, which is after year 14, we get 2 times 2M this time, or 4M. Then after 7 more years, after 21 years total, we have 2 times 2 times M. So you can see a pattern. So we'll write this, we'll start with this one. We'll think of this as M times 2. This one as M times 2 to the second. And this one is M times 2 to the third. And then working backwards, okay, M times 2 is M times 2 to the first. And since 2 to the 0 equals 1, we can write the value, the beginning value is M times 2 to the 0. Then we do the sort of thing that we did in the previous example. We'll start with M times 2 to the first. After the 7th year, the value is M times 2 to the first. So we can think of this as M times 2 to the 7 divided by 7. 7 divided by 7 is 1. After 14 years, the value is M times 2 to the 14 divided by 7. 14 divided by 7 is 2. And then after 21 years, the value is M times 2 to the 21 divided by 7, because 21 divided by 7 is 3. So after T years, the value of the investment is M times the base number 2 raised to the exponent T divided by 7. It's pretty neat. Okay, we'll look at a couple more word problems. They might qualify as applications, maybe not. Okay, so on this one, an exponential function has the form y equals a times b to the x. Notice that the exponent x applies to b only. It doesn't apply to a. Okay, and the base number b is greater than 0 and not equal to 1. And if the graph of the function passes through the points 1, 12 and 2, 4, find the values of a and b. Okay, so I'll just rewrite y equals a times b to the x. And this is more detail than is necessary, but I'll write when x is 1, y is 12. So in this equation, we replace y with 12 and replace the exponent x with 1. So 12 equals a times b. Then, when x equals 2, y equals 4, that's the information we get from this ordered pair. So in the function, replace y with 4 and replace the exponent x with 2. There's more than one way to go about solving for a and b. We know that none of the numbers could possibly be 0. I mean, that's stating the obvious. So one thing we can do, since I have 12 equals a times b and 4 equals a times b squared, I can divide the left-hand side of this equation by the left-hand side of that equation, provided that I divide the right-hand side of this equation by the right-hand side of that equation, if you see what I mean. So I'm going to divide 4 by 12, 4 divided by 12, and I'm going to divide a times b to the second by a times b. Okay, the a's cancel. A divided by a is 1. B to the second divided by b is b. And 4 divided by 12 is 1/3. So b is equal to 1/3. Another way to do it, which is perfectly fine, it just takes longer. You can solve each of the two equations for a. So over here, I'll just write how to do that. If you solve this equation for a, you get a equals 12 divided by b. Solve the other equation for a, you get a equals 4 divided by b to the second. And by substitution, since a is 12 over b and a is 4 over b to the second, you can write 12 over b equals 4 over b to the second. And then you could use cross products or equal 12 times b to the second equals the other cross product, 4 times b. And then divide both sides by b and divide both sides by 12, you get b equals 1/3. So either way is okay. But we also want to find a, so use either of those equations and replace b with 1/3, and then multiply both sides by 3, and we get a equals 36. So the function is y equals 36 times the base 1/3 to the x. And if you're nervous about the outcome of your results, you can always test it using the ordered pairs. Okay, the next example is the same sort of problem. An exponential function has the form y equals a times b to the x, where b is greater than 0 and not equal to 1. And the graph of that function, y equals a times b to the x, passes through the ordered pairs 280 and 320. Okay, so y equals a times b to the x. And when x equals 2, y equals 80. So replace y with 80 and replace x with 2. So we get 80 equals a times b to the second. And then the other ordered pair, when x equals 3, y equals 320. So replace y with 320. Set that equal to a times b to the third. And then we can solve this in using either of the methods that we did before. So it looks like if I do the division method, if I divide the left-hand side of this equation by 80, 320 divided by 80, and divide the right-hand side of this equation by the right-hand side of the other equation, a times b to the second, then I just get 4 equals b. And if 4 equals b, then 80 equals a times 4 to the second. And then 80 divided by 16 is 5. So the value of a is 5. And so our function is y equals 5 times 4 to the x. Here there's about a little more than, or a little less than 5 minutes left. We'll go ahead and start section 3.3 on logarithmic functions. Okay, so we'll start in objective 1. The objective is to convert between logarithmic and exponential forms. Okay, but we'll sort of review in the process. Let b be a constant real number such that b is greater than 0 and b is not equal to 1. And then recall that y equals b to the x is the base b exponential function of x. Also remember that the domain of this function is all real numbers from negative infinity to positive infinity. And its range is the set of all positive real numbers, or from 0 to infinity, but excluding 0. So you might have picked up on the fact that every time that we graphed an exponential function, it passed the horizontal line test. So it's a one-to-one function, which means that its inverse is also a one-to-one function. And so it turns out that the inverse function of y equals b to the x is the base b logarithmic function y equals log base b of x. So we know something about the domain and range of the inverses. So if you remember, since y equals log base b of x is the inverse function of y equals b to the x, it follows that the domain of y equals log base b of x is all positive real numbers from 0 to infinity. Its domain is the same as the range of its inverse. And the range of y equals log base b of x is all real numbers. That's the same set of numbers as the domain of its inverse. We learned that from section 3.1. Okay, the definition of log base b of x. Log base b of x is the exponent that the base number b is raised to in order to produce x. So if you can remember that logarithms are exponents, that will be helpful. So if we mimic this definition, log base b of x is the exponent that b is raised to in order to produce x. Okay, so if we raise b to the exponent log base b of x, it produces x. This is one of the properties of logarithms that you'll encounter, but it's just the definition written as an equation. So this reiterates what I just said. Base b is raised to log base b of x, and it produces x. Okay, we have a little over a minute left. So, all right, I'll mention this thing, and I'll remind you of this sort of on a repeated basis. Just think of capital B as a base number, so it's positive and not equal to 1, and let capital A be greater than 0, and let P be any real number, positive, negative, or 0. Then these two equations are equivalent. Log base B of A equals P. It's a logarithmic equation, but it's equivalent to this exponential equation, B raised to the exponent P equals A. So knowing how to switch from a logarithmic equation to an exponential equation that is equivalent is sort of an important thing to know how to do. But you can look at this logarithmic equation. Notice the base number b of the logarithm. Remember, logarithms are equal to exponents. So p is an exponent. So b raised to the exponent p equals a. That's what we see in this exponential equation. Okay, it's time to quit. I'm going to go to my office and start the Zoom meeting. So if you'll show up at the Zoom meeting, we can talk about how to use Zoom meetings for proctoring quizzes and tests.